Hi everyone, today I'm going to be walking you through the gravity-dependent dissolution model. This is a G-Space platform demo showing how dissolution behavior can be modeled and compared under Earth gravity, microgravity, and custom gravity conditions. So if someone asked us to visualize the dissolution process, we could probably think of something like this video was showing, where we drop a tablet into water and we slowly watch it dissolve. But here's another question. What happens when gravity is removed? If we can't go to space and experiment, the best tool we have to visualize this process is to build a simulation model to understand how dissolution works in microgravity. How do we build such a model? Setting up the simulation. So first we establish that we are working with a tablet of radius r, height h, and density rho s. This tablet is released into a volume of water that is much larger than the tablet itself. From Noyes-Whitney dissolution kinetics, we derive that dissolution time in 1g is proportional to r, while dissolution time in 0g is proportional to r squared. Walking through the physics. So in 1g, the tablet sinks to the bottom due to gravity. Once in contact with the water, the tablet undergoes a two-step chemical dissolution reaction, as shown in the two equations on the left. Buoyancy convection causes bubbles to rise to the surface and are eventually released at the water-air interface. The entire dissolution process in 1G is driven by diffusion and convection of the bubbles in the liquid. So now that we understand the 1G physics, we're able to capture it in the synthetic video as shown on the left. But now we have new questions. How long will it take for a tablet in varying environments to dissolve? We know that the big difference between 0G and 1G is that without gravity, 0G dissolution is only driven by diffusion. So we aim to capture this physical process in the simulation. So here is what the simulation demo looks like. Currently we are in 1G and we can see the synthetic video that depicts 1G dissolution. We have a results panel that shows that dissolution time is predicted to be 10.9 seconds. And we also have a bunch of graphs that show different statistics, such as boundary layer, CO2 release rate, tablet radius over time. Now, keeping everything fixed, we change the gravity condition to 0G. Once we run the simulation, we can wait to see what happens. So we now have a different kind of synthetic video in 0G where we can see it takes much longer for the tablet to dissolve. Dissolution time can be seen to be 278.3 seconds. And again, we have a panel of different graphs that show different statistics about the tablet dissolution over time. So now what happens if we now simulate in 0G but with different conditions? So here we're going to change the median bubble size to 0.0005. We're going to change the bubble size spread to 1.45, and we're going to see what happens. Here we can see that there's a much wider variety in bubble size in the synthetic video. We can also see that dissolution time has actually decreased from around 278 seconds to 234 seconds. We still have the same panel of graphs that show different statistics over time. Now what happens if we change gravity to lunar gravity, which is 0.16 g? We can see that the dissolution time has starkly decreased to 17.4 seconds. And we can also see all the statistics relevant to this in this graphing panel. Now we can also see what happens if we change gravity to Mars gravity, which is 0.38 g. We also change the median bubble size back to 0.001 just to see what that looks like. The bubbles are now a lot larger but still have the same variety. The solution time is 14.2 seconds, which is lower than both lunar gravity. And we can again see all different kinds of statistics. So how did we verify our dissolution model? As I said before, we derived dissolution time equations from Noyes-Whitney dissolution kinetics. And from this, we know that in 1G, dissolution time is proportional to R, while in 0G, it's proportional to R squared. Therefore, we expect that when we vary R, we can expect the log of dissolution time against the log of R to adopt the slopes of 1 and 2. So we can see in 1G the slope we observed was actually 1.25, and we can attribute this to variance in the boundary layer that surrounds the tablet. In 0G, the slope was 2, which matches our expectations according to Noyes-Whitney kinetics. So how do we verify our model further? It turns out that an experiment on the ISS has actually been performed, and our model is within 1.5 times within the observed dissolution time. In addition, our model also allows users to play around with different variables and capture different dynamics. Because the tablet is not fixed in this ISS videos, bubbles are released due to momentum conservation, making the tablet rotate. This rotational process is Marangoni convection and helps with the removal of bubblets from tablet surface. Marangoni convection is an addition we will be adding soon. So for now, we established a temporary variable to match the ISS observations called eta. So if we check this box to calibrate dissolution time to the observed ISS time, we can make the dissolution match what we observed in the video. So now the dissolution time is around 190 seconds, and we have a new variable called eta, which is 1.465, and it essentially absorbs any unaccounted for Marangoni convection physics. Again, we have this panel of graphs that we can see how the dissolution statistics work over time. In the simulation, we aim to help users capture the difference between dissolution in 0G and 1G, and we allow users to manipulate the gravity conditions as well as the experimental setup.